and have cracked different PSU exams. So if you want to prepare for PSU exam, that also can be discussed in the separate session. And my area of expertise is EMFT, which is also known as EMT, electromagnetic theory, electromagnetic field theory, communication system, signals and system, advanced communication system. Okay, so these three usually comes in GATE. Okay, these three comes in GATE, and for double E and IN students, EMFT and signals are also there. And for electronics student, there are some extra portion in the EMFT, some portion which is common, and there are some portion of EMT which is separate from the double E and IN syllabus. So in the today's lecture, we are taking one topic from the magnetostatic. Okay, because in the GATE syllabus for the double E, EC, and IN, the common portion is electrostatic and magnetostatic, which we have learned in our plus 2. Okay, in the class 12, if you have prepared for JEE, then definitely you will have gone through these topics. So that's why I told that you must be familiar with the topic that we are going to discuss, but with the different angle. And because you are a little bit familiar about these topics or the word associated with the topic that we are going to discuss, I will guide you and I will make you learn the things such that you will be able to solve the GATE question by the today itself. So let's begin with the first topic, which is Biot-Savart's law. And I have kept the background black today, but in the regular classes, it will be a white background. So if suppose you might be thinking of getting these like PDF downloaded and for your notes and you want to take print out, then you will not have to get worried. So Biot-Savart's law, all have heard about it. Okay, all have heard about the Biot-Savart's law. Yes. So because everybody knows the Biot-Savart's law, the basic definition, if I want you to recall this, then the law says, Biot-Savart's law states that the magnetic field intensity, because whenever we have a current through the conductor, magnetic field produces. Suppose we have a conductor like this, then when this current flows through this conductor, the magnetic field will be generating around this conductor, okay, in the circular way. So what is the magnitude of magnetic field? What will be the value of magnetic field strength? We want to calculate in these different points. And for this, we have, okay, for this we have a Biot-Savart's law. So Biot-Savart's law states that differential magnetic field intensity DH produced at a point P by the differential current element IDL is proportional to the product IDL and sine of angle alpha between the element and the line joining P to the element, and is inversely proportional to the distance R between P and the current element. Now, if you go through this statement, there are many words that has been used, and you might think of what it is written. It is not that much understandable. So for this, I'm here. I will tell what it wants to say. Suppose this is a conductor, and because the current is flowing through this conductor, it is I, and magnetic field will be generated around it. So that magnetic field we want to calculate at point P, which is some distance from the conductor. Now, we want to say that if I want to calculate the magnetic field intensity because of the small length of the conductor, not the complete length, I want to calculate the magnetic field only because of a small length of conductor, that is this red line. This is the small element of the conductor and the current flowing through this is I. So that is why we call this as a current element IDL. This is what it is written. Differential current element ideal. Differential current element ideal. So this is how this current element comes in the law. Now, because of this current element, we want to calculate the magnetic field at point P, which is making an alpha angle, which is making an alpha angle with the current element. So if you join the line from the current element to the point of interest where you want to calculate the magnetic field, okay, then this distance is called r. The distance at which you want to calculate magnetic field is the distance r. So now the magnetic field intensity dH. Why we call it dH? Because we are calculating magnetic field because of small length. So that is why we are calling it as a differential magnetic field. It is proportional to the current element, product of current element ideal and sine of sinusoidal sine of angle alpha between the element, this red current element, and the line joining P. So this is the line joining P. So the angle between the line joining and the current element is alpha. Sine of angle between them, that is ideal sine alpha, it is directly proportional and inversely proportional to the distance r between the point P and the element. So this current element with this point of interest P, the distance between these two, it is inversely proportional to that distance. So this is how we define the Biot-Savart's law. Okay. Now we use the proportionality constant K, and that will become K IDL sine alpha upon R square. And K is the proportionality constant, which is having the value 1 upon 4 pi. So the final value of magnetic field at point P will become IDL sine alpha divided by 4 pi R square. This is the magnetic field intensity because of this small current element. Now, if you suppose want to calculate the total magnetic field because of the whole conductor, then what will you do? You will take one small element here, then you will take one small element here, then you will take one small element here, one small element here, one small element here, and add them all. That means you are going to integrate, because integration means addition. So what you will do? Integration of dH, which will give you H, is equal to integration of IDL sine alpha divided by 4 pi R square. This will give you the total magnetic field at point P because of the conductor having the current I. Okay, so this is how we define the Biot-Savart's law. So there is still one thing which we haven't defined yet, that is known as the direction. Because we have defined the magnitude, but we haven't defined the direction of magnetic field. So the direction of magnetic field, because we define the magnitude, if you include the direction, then that will become vector form. And magnetic field intensity is a vector quantity. Okay, magnetic field intensity is a vector quantity. Clear? Now, how do you define the direction? So to define the direction, we have written over here IDL and the cross product. We have written the cross product here, the cross product and AR, that is a unit vector AR. So what is the cross product? This is a cross product. So how do you write the cross product? So suppose these are the two vectors A and B, then what is the cross product? Magnitude of A into magnitude of B and then sine of angle between them. Okay, A and B is having the angle alpha, then sine of angle between them. Similarly, if I am writing I, in fact, I should say I am writing DL only. I is not the vector quantity. DL cross AR. So what does it mean? Magnitude of DL, magnitude of AR, okay, magnitude of DL vector, magnitude of AR, and sine of angle between them. So DL is nothing but a length, so its magnitude will be DL. AR is nothing but a unit vector. Unit vector will have the magnitude 1. What do you mean by unit vector? Unit vector is the vector which has magnitude 1 and sine alpha. So DL into sine alpha. So DL into sine alpha can be written as DL cross AR cap. So that is what here we have written. DL into sine alpha was there in our expression. So this DL sine alpha I have written as DL cross AR. So this is the DL vector and AR. This is a DL vector. Now AR is the unit vector. How do you write the unit vector? Unit vector is given by the vector divided by its magnitude. Vector divided by its magnitude. So this is the vector R and divided by its magnitude. So magnitude is written simply as R. Magnitude is written by simple light light phase. So that is R. So this R was already there, R square, and this R multiplied, so it will become R cube. So magnetic field intensity for a small current element, in this diagram, this is the small current element. Because of this current element at point P, magnetic field intensity in the vector form will be given by this expression. Now, why I have written the vector AR cap? Because it is in the direction of R. The line joining is in the direction of R. So that is why we have written this AR cap. AR cap is the unit vector. It will not change our expression. And this DL sine alpha can be represented in the form of AR cap. Now, because we want to calculate its direction, so to calculate the direction of magnetic field, we have right hand thumb rule. The right hand thumb rule says, if the thumb of right hand pointing in the direction of flow of current, if the thumb of right hand pointing in the direction of flow of current, then the finger encircling the conductor will become the direction of magnetic field. Okay, now let's understand this by this diagram. Suppose this is the conductor having the current I. So now thumb is pointing in this upward direction. Okay, thumb will point in the upward direction, and when you curl your finger, the right hand finger, so that will be in this direction only. When you curl your finger in the back side, it will be like this. In the back side of this conductor, it will be like this, and when you come in the front, it will be, and this is suppose thumb. Okay, this is your thumb. So you can imagine now, if it is thumb, then thumb is in the upward direction, and then this is the finger encircling. Okay, this is the finger encircling. So this circular path which is generating around this conductor like this, will give you the magnetic field. Now, because this finger encircling gives the arrow like this, and here it is like this, and now it is like this. this point P, which is written over here, is similar to the point P which is kept in this side. In the right side of the conductor, there is a point P. Now, if you follow this arrow, this follow is going inside this point P. This arrow will be inside this point P. That's why the cross is shown. Because when you keep your right hand finger on this point P, when you keep tip of right hand finger in this point P, then this point P is going inside the screen. And if it is going inside the screen, that means it is inward. That's why the magnetic field will be inward. Now suppose there is a point Q in the left hand side. Then when you encircle your right hand finger, and when you see the tip of your right hand finger, it will be coming out from this. It will be coming out from this. So when it will come out, it will be represented by dot. It will be represented by dot. Okay. So now you can see here in this diagram, you can understand that right hand thumb rule here easily. This is the thumb, which is the direction of current. Okay. And finger is in the direction of magnetic field. And finger showing this will be the direction of magnetic field. Right? Getting this point? Now you can easily visualize it. The thumb is in the upward direction and finger as in circling. When you keep the point of interest here, the finger will be outside, and when you keep the finger here, then it will be inside, that is cross. Okay, and this is also the screw rule. Screw rule also be can also give you the direction of magnetic field. If you tight the screw and if it goes in the direction of flow of current, then the way you are tightening it or you are rotating it become the direction of magnetic field. Though we usually prefer this one in our calculation, because in the gate examination they will ask you the direction as well. So the right hand thumb rule should be very much clear to all of you. Let me know if it is clear to all of you. Tell me, is it clear? George? Yes. So any doubt up to this point? Very basic thing we are discussing, but it is the syllabus of gate. Now we have the line surface and the volume current. So let's skip it for time being. We go directly to this point. Yes. For timing, let's skip it because that is not having much concept. Now, because in the previous discussion, the Biot-Savart's law is not restricted to the shape of the conductor. It is not restricted. Means it can have this shape, it can have straight line, it can have circular. In all this conductor, the current can be flow, and because current can flow through this conductor, we can calculate magnetic field intensity at any point. So the Biot-Savart's law is not restricted by the shape of conductor, but this is the special case of the Biot-Savart's law, where we are saying that straight current carrying conductor. So this time your conductor should be straight. It cannot have any arbitrary shape. It cannot have an arbitrary shape. It is a straight conductor, and it is very important in the gate examination. Okay, so this is the length of the conductor. It is a finite length. Okay, the length is finite, which is from A to B. that is the finite length conductor, and having the current I. Okay, that is having the current I. So it is a finite length conductor having a current I. Clear? We want to calculate the magnetic field intensity at point P. We want to calculate the magnetic field intensity at point P. That is our aim. Now, whenever you see the straight conductor in your question, we have a specific formula that we will derive in our regular classes, the derivation part. But in this class, we will directly come to the result and we will learn how to apply that formula in question. Because important thing in the GATE exam is, first, basic fundamental concept should be clear, and second, you should be able to solve the question if you want to crack it. Okay, if you know the concept and if you are not able to solve the question, then also it doesn't work. So right now we will directly write the formula, but only knowing the formula also doesn't work, because the values in the formula, how do you calculate those values, is itself very important to understand. So the formula is this. Here the terms, let's see once, and then we will go back to the diagram and we'll understand what it denotes. The magnetic field intensity H, it is a magnetic field intensity H for a straight conductor having current I, this is the current I, divided by 4 pi rho. Rho is perpendicular distance. Rho is perpendicular distance from conductor to point of interest. Remember the way I am writing, conductor to point of interest. So you have to draw the perpendicular line from conductor to the point where you want to calculate the magnetic field intensity. Then alpha 2. Alpha 2 is angle subtended by upper end of the conductor to the line joining between upper end and point of interest. Okay, and alpha 1 is the angle subtended by lower end. I will show all this in the diagram of conductor, and the rest of the things are same. Then A phi. A phi will give you the direction, because this is A phi gives you the direction. It is unit vector. A phi is the unit vector, so it will give you the direction. So A phi is a unit vector which gives direction. Direction of magnetic field. Okay, now let's go back to this diagram. This is the finite length conductor. What I said, rho is this one. Now I have written that rho is the perpendicular distance from conductor to point of interest. So this is the conductor and this is our point of interest. So if I draw the perpendicular line from point A, it will go here only, this one 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 only. These are the points where I can draw the perpendicular line. How can I draw the perpendicular line from point A to point P? Point A to point P, there is no perpendicular line can be drawn directly. So in such cases, when you are not able to draw directly because it is not coming in the same line, or you can say in the parallel to the same conductor. Parallel to the conductor, it is not lying. This point P is not lying between A to B. So if this point P is not lying between A to B, then you cannot draw the perpendicular line directly from the conductor. So now what you have to do is you have to extend the axis of conductor. So you extend the conductor axis. The axis in which conductor lies. The axis in which conductor lies is called conductor axis. So that axis you have to extend. So I am extending the point A downwards. Okay. Now I have extended. When I extended, I reached to this point O, which is origin. It is not necessary to have origin, but here this diagram is drawn in such a way that O is the origin. But forget about origin, it is not necessary. So if when I extended it, I get the point O, from where I can draw the perpendicular line to my point of interest P. I can draw this perpendicular line to point of interest P here. Now you can understand easily that if there is a conductor A and B, and if the point P is lying somewhere here, suppose, then I will have to extend in either direction and then draw the perpendicular line from conductor, because we cannot directly from the conductor, so we will draw from the conductor axis. So we will draw from the conductor axis to the point P. So this will become 90-degree, and hence we will call it as a rho, because rho is the perpendicular distance. So this is the first term which you understood in the formula. So you can understand that how important it is. It is taking time to understand the formula itself. So when we derive, it will again take some more time. So to save the time and to tell you that how you can solve the question through this formula, I am skipping the derivation. Okay. Now we have understood the rho. Now when you extend it from the lower end, there is an exterior angle formed by the extension of the conductor to the line joining between the lower end and the point P. So I will join the line from the lower end. I will join the line from the lower end to the point of interest. I will extend my lower axis, lower point, and then I will calculate exterior angle. Listen carefully, exterior angle. Okay, you are not going to calculate this angle. This is interior. I am calculating that angle when I am extending the line. So that is why I am calling it as an exterior angle. So that line joining will make angle with the conductor axis. Exterior is called alpha 1. Now you will take the upper end of the conductor. You will again join the line. From the upper end to the point P. That's why in the formula I had written lower end and upper end. So the upper end will again join the line from point P to this upper end, and this time this angle is interior angle. This is an angle subtended between the conductor and the line joining between B to P, upper end to point of interest. The angle subtended by the line joining between upper end and point of interest and the conductor is called alpha 2. Okay. So you have now got all the points Now you are able to calculate the magnitude of magnetic field. Let me know if you have any doubt in any particular term. What we have understood, rho, we have understood alpha 1, we have understood alpha 2, and the current flowing through the conductor is I. That will always be given. That will be given in the question, because without current, they will not ask about the magnetic field. Tell me if you have any query in the diagram. Yes, formula I will show it. Yes, this is the formula. Angle subtended by, I will just change the statement. Angle subtended by conductor. Angle subtended by conductor and line joining between upper end of the conductor and point of interest. Yes. So anything you want to ask here? Formula, George, it is clear. Aditya. So I is clear, rho is clear, alpha 2 and alpha 1 is clear, and A phi. A phi can be calculated by right hand rule. A phi can be calculated by right hand rule, or there is a mathematical formula also by which you can calculate. That is AL cross A rho. The cross product formula you can use. Suppose you are not able to apply the right hand rule. Sometimes it is not easy for all of us to imagine that, because you will apply the right hand formula. That means you have to curl your fingers, you have to see the thumb. So sometimes it becomes difficult to calculate by the right hand rule. The diagram is given in that way that we could not apply the right hand rule. So in that case, what you can do is you can apply it mathematically. So how you can calculate this A phi? Then I have written AL. Now the question is, what is AL? So AL cap is unit vector. So that is nothing but a unit vector in direction of current. Unit vector in the direction of current. So the direction in which current is flowing will become the unit vector AL. And A rho is very much clear, because rho means perpendicular distance. So A rho cap means the unit vector in the direction of perpendicular distance. So unit vector in direction of rho. The direction in which you draw the rho will become the arrow cap. Okay. Now I will make you understand this. Suppose this was the conductor, straight conductor. These are the axes. This is suppose Z axis and this is suppose X axis. And the conductor is clear. The conductor is A to B. The length of the conductor is AB. The current is flowing through this. Now, in which direction current is flowing? Can you tell me? The current is flowing in which direction? Current is flowing in which direction? Current is flowing in which direction? Comment in the comment section. In which direction you can see the current? Yes, along the z-axis, as you can see that it is moving upward. So if it is origin, that is 0, then if it is moving upward means we can say that it is positive z-axis because it is upward, the positive z-axis. So the AL will become plus AZ cap. That is the unit vector. Okay, or sometimes you can also write it as K cap. Along the z-axis, the unit vector is ijk. I is for x-axis, j is for y-axis, and k is for z-axis. So we can represent az cap, or we can also write k cap. Our point of interest was P here. Now you tell what is the perpendicular distance from the conductor to point of interest. So that is the direction in which you draw the perpendicular line, which was rho. Now you tell me what is a rho cap. What do you think? What should be a rho cap? In which direction you have drawn the perpendicular distance? In which direction you have drawn the perpendicular distance? Yes, it is positive x-axis. When you draw the perpendicular line from origin to point P, you are moving from origin to point P. That means you are moving in the positive x-axis. So now we will say this as a plus AX. Okay. Now what is the direction of magnetic field? I will substitute these value. AL means AZ and arrow means AX. AZ cross AX, it is AY. It is AY. I hope that unit cross product you all are aware about it. Well, in our regular lecture, when we start, we will start from the vector calculus itself. So we will discuss all this cross product, dot product, and the different coordinate system. But I'm expecting that you know this because this is very basic thing. We all know I cap cross j cap is k cap, j cap cross k cap is I cap, k cross I is j, and when we change the cross product, then it will become minus. Okay, so we get y, and if you see the axis, then you can see where is the y-axis. This is x-axis, then inside this is the y-axis, and this is the z-axis. This is x, this is x-axis, this is y-axis, and this is z-axis. And when you apply the right hand rule, we have already calculated this, and we said that it is cross because the magnetic field lie inside, and when you go inside, this is the positive y-axis. Coordinate system also we will discuss. So why the y-axis is inside, that also we will understand. But for time being, I am saying that this is the coordinate system. If this is x-axis, this is y-axis, and this is z-axis. And when I am calculating by mathematically by magnetic field, so this is AY, which is positive AY. Positive AY means it is in the inside the screen. So inside the screen also we get when we apply the right hand thumb rule. So right hand thumb rule, when we applied the thumb pointing in the direction of current, then this point P is nothing but magnetic field inward. So magnetic field is inward. Clear? Is it clear to everybody? Yes. So now you have understood the formula And I will give you one question related to this. Let's go through the question. Okay. Let me go through the question. Okay. Let's solve this one. One question I will tell, and then another question you try to solve. Okay. See, a square conducting loop of side 2a in the z is equal to 0 plane. Z is equal to 0 plane means xy plane. Z is equal to 0 plane means xy plane. Z equal to 0. So that means it is xy. So suppose this is xy plane. This is x-axis and this is y-axis. Okay, this is x-axis, this is y-axis, this is the center, 0, 0. And the conductor is having the current I in the counterclockwise direction. So in this direction, the current is flowing. In this direction, in this direction, in this direction. Okay. We want to calculate the magnetic field at the center. That means at point O. Now, if you will see this conductor, it is a circular conductor. It is a closed loop conductor. Okay, square conductor and forming a closed loop. Now, in such type of case, because it is conductor, can you find any straight portion in this square loop? Can you see the straight part of this conductor? The straight part of the conductor is A to B. If I divide this conductor in the 4 different segments, then A to B is the straight part, then B to C is another straight part, C to D is another straight part, and D to A is another straight part. So I can take this question as 4 straight conductor placed in the different way, placed in the different way. Okay, so I will calculate for conductor AB. Okay, I am dividing this in the 4 different part. I am taking AB as a single conductor. So how do you calculate then for conductor AB? The current is flowing in this direction. The current is flowing in this direction. Then we have to draw the perpendicular line. So we will draw the perpendicular line from conductor to point of interest. So we want to calculate at O. So this will be my perpendicular distance, which we denote it as rho. Here and here it is rho only. No? Okay, rho. Correct. Now it is exactly from the center. So this will become A because the total side of the square is 2A. So this part, let us say M. So A to M is A and M to B is again A. So the total distance will become 2A, right? In this way. So I will need this space. So I am rubbing it. Okay. Now, when I am erasing it, now, this is the perpendicular distance. So it is 90-degree angle. Fine. This is 90-degree. Correct. Now, from the lower end to point of interest, we have to join the line. From the lower end to point of interest, so we have joined this line. Now we have to extend the lower end. We have to extend the lower end. In every question, you have to extend the lower end. So extend this lower end. Now we have seen that alpha 1 is the angle subtended from the lower end. Okay, alpha 2 was from upper end, alpha 1 is from the lower end. So alpha 1 is from the lower end. So what is the lower end? The lower end is in this question point A. This is the point A, the lower end. So we have extended this. Now exterior angle, I said exterior angle will become alpha 1. So this outer angle is alpha 1. Now again you will join the line from the point of interest to the upper end. So this is the line joining from the point of interest to the upper end. Now, interior angle was alpha 2. So this is alpha 2. So have you got this value alpha 1 and alpha 2? Now can you tell me what will be the value of alpha 1? What will be the value of alpha 1? What will be the value of alpha 1? Anyone? See? The side A to B, AB and AD both are perpendicular, na? Square. It is forming a square. So both are perpendicular. And I am joining the line exactly from the center. So it will divide both in 45 degree. Okay. So this will be 45 degree. And if it is 45 degree, then remaining will be 135. Okay. What about alpha 2? The alpha 2 is interior angle, that is 45 degree only. Now we have left with rho. What is the value of rho? Suppose I apply 1045 in this diagram, then 1045 is rho upon A, which will give us rho is equal to A into 1045. The value of 1045 is 1, that means A. Now what is the formula? Magnetic field due to AB. Only due to AB we are calculating, na? Only due to AB is I upon 4 pi rho, that is the formula, cos of alpha 2 minus cos of alpha 1 and the direction Fi. So I is I only, rho is A, cos alpha 2 means 45, cos alpha 1 means 135 and the direction A rho, A phi. So this is I upon 4 pi into A, 1 by root 2, cos 135 is minus 1 by root 2, so minus minus become plus and A phi. So finally, we will get 2 pi A into root 2. Okay, this is 2 upon root 2 and 2 and this 4 will get cancelled. So 2 pi A root 2. Now the direction. The direction is calculated by A rho, AL cross A rho. You tell what should be the direction. AL cross A rho. Direction of flow of current. Direction of flow of current is right side. Right side means x-axis. So it is AX. Direction of perpendicular distance. Perpendicular distance from conductor to point of interest. That's why the line, the arrow is important. When you draw the perpendicular line, arrow is important because if you take the perpendicular distance from O to M, then the direction you will take will be minus y. But here we have to draw the perpendicular length from M to O. M to O is in the upward direction and the upward direction is y. So AX cross AY is AZ. So magnetic field will have the direction AZ. So this is the magnetic field intensity because of the side AB. Clear? Is it clear? Okay. Now you can see that this is AZ, this is AZ, this is AX, this is AX. So definitely these two options will be eliminated because the direction will be definitely Z. But still, this is not the answer. You cannot say that option C is correct because we have got this. No, this is only because of the one side of the conductor. Only one side of the conductor. Our whole conductor is completely square, but we have calculated only for conductor AB. Now you have to calculate for BC. Now if you see the BC, then B is the lower end. Again, you will extend this lower end. You will form this outer angle. This outer angle will be 135 and this is your upper end. of the conductor. You will join the line and you will calculate this inner angle. This will be 45. So outer angle is 135. So alpha 1 will be 135. Inner angle is 45. So alpha 2 is 45. So these two things are going to be same for BC also. Now, perpendicular distance from the conductor to point of interest, suppose this point is N. So conductor to point of interest, when you will draw this perpendicular line, then this will become your rho. Okay, and this is your 90 degree. This is your 45 degree. This complete length is 2a. This complete length is 2a. So half length will be a. So this length will be a. This length will be a. Again, when you apply the 1045 here, the rho will be equal to a. Rho will be equal to a when you apply the in this triangle. In this triangle, when you write 1045, you will get a. So rho is equal to a also same. So the magnitude is same because everything is same except a phi. Till now, whatever we discussed, alpha 2 came out to be same, alpha 1 came out to be same, rho same, current is also flowing same. So the magnitude I upon 2 pi a root 2 will be definitely same. Now the direction. Now let's calculate the direction for BC. Calculate the direction for BC. Okay. So direction of flow of current in BC. Direction of flow of current in BC is AY because it is flowing in the upward direction. Direction of flow, direction of perpendicular distance. Perpendicular distance from conductor, that is this point to this point, conductor to this point, conductor to this point, O, N to O, N to O. Which direction you are going? Left side, N to O, N to O, N to O, left side. So left side means minus x-axis. So AY cross minus AX is plus AZ only. So this is also giving the same direction. So that means everything is same for BC. So when you will go through this, AB, BC, CD and DA all are going to be same. Okay. So because it is symmetrical, now the conclusion is whenever there is a symmetrical polygon and you want to calculate magnetic field in the center, then you don't need to calculate for each side of the polygon. You have to calculate magnetic field only for one side and multiply it by the number of side. So total magnetic field H at the center of this loop will be 4 times of magnetic field because of one side. So one side we have calculated as I upon 2 pi a root 2 az. When you solve it, you will get option A. Okay, option A will be the right answer. So this is only because of one side. Okay, it is the value which is given in the option only because of one side. When you multiply it by 4, because it is symmetrical, so the number of side it is given, you have to multiply by that and then you will get the correct answer. Clear? Is everything clear? Just let me know once in the chat section. Any doubt? Right. So in this way, you have to solve the question. Okay, this is the question for you. If you have pen and paper, would you like to solve it? Don't bother about that it is open. It is actually a closed loop only, and that current is flowing through this. That current I is flowing. Okay. You can see that it is again symmetrical and you have to calculate at the center O. And suppose this is A and this is B, this is C, this is D, this is E, this is F. And I will also give you one hint. Maybe some of you know, but some may not be knowing about this. So that's why I am going to tell this. This angle is 120. Okay, this angle is 120. This is forming a hexagon, a regular hexagon. It is clearly written. The side is 1 meter. So this side is 1 meter length. This side is 1 meter length. Now you have to calculate magnetic field in the center. What will you do? At least you tell that what you are going to do. Because current is flowing in this direction, the point where the current starts become lower end, the point where the current terminates become upper end. So we will have to extend the lower end. As I told, every time you have to extend the lower end and join the line from lower end to point of interest. Similarly, join the line from upper end to the point of interest. This angle is your alpha 1 and this angle will become alpha 2. What is the value of alpha 1 and alpha 2? What is the value of alpha 1 and alpha 2? (120 and 60). Okay. Alpha 1 is 120, correct? Alpha 2 is 60, that is also correct. Now we have to calculate this perpendicular distance. So we will draw this perpendicular distance. Okay, so that will become conductor to point of interest. So conductor to point of interest, that will become rho. What is the value of rho? What is the value of rho? Also calculate the value of rho. Calculate the value of rho. We have to apply 1060. I will write here. 1060 is equal to height, that is rho, divided by base. Base is how much? It will be 0.5 because the total side is 1, so it will divide equally. So this is 0.5. So rho will be 0.5 root 3. 1060 is 0.5 root. Okay. Now we can write the magnetic field AB because we need to calculate the magnitude only. So we don't bother about direction. The formula is I upon 4 pi rho cos of alpha 2 minus cos of alpha 1. Current flowing is 1 ampere. So 1 upon 4 pi root 3 by 2 because 0.5 is 1 by 2. So root 3 by 2. Cos of alpha 2 you said 60 minus alpha 1 which is 120. So it is 1 upon 2 pi root 3. Cos 60 is 1 by 2. Cos 60 is 1 by 2 minus cos 120 is minus 1 by 2. So finally we will get, this will become 1. So 2 pi root 3. So this is the magnetic field because of AB. Is it the final answer? 1 upon 2 pi root 3 is the final answer, or anything else which is left? Multiply by 8. No, I think this is the hexagon written, so multiply by 6, isn't it? T upon pi root 3. Okay, so final answer is coming out to be 0.5513 and magnetic field, so ampere per meter. Multiply by 7. Now you will say multiply by 6. Okay, so read the question also. Now, 0.55 is the answer. How many of you have got this solution? If you have any doubt, is it clear? Every step is clear to all of you? Are you able to solve such type of questions? Will you be able when you will see this type of question next time? Straight conductor should be there. When you form any particular shape, then there should be a straight conductor. Through the straight conductor, you will be able to calculate the magnetic field using the formula. There are certain things that you have to keep in mind: the value of alpha 1, alpha 2, and rho. That is it. If you know these three things, how to calculate, then you will be able to solve this question. Got it, everyone? Aarti? Yes? Now, I would like to tell that this is the question from the GATE examination. This is the GATE question, and year I don't remember exactly. It is around 2016-17 somewhere. 2016-17. So this type of question comes in your examination, and if you are able to understand this, then you can see that when you attend all the classes regularly, then how much comfortable you are going to be in your GATE examination questions. Okay, so these are all GATE questions. This is also GATE question, but and this is also a finite length. This is also a straight, but along with the straight, it is infinite also. So that can all not be covered in everything in the demo class. So that is the overall idea I have given you. I hope that after attending this lecture, you are much confident that when you attend the overall class, you will be able to get the good score in the EMFT. So, how many of you from the electrical, may I know? Students from the electrical. Student from the electrical. Uh, George, about this, Dinesh sir will tell that how the subject is going to be. Okay. EC students will have little bit less weightage in this part of uh, syllabus that we discussed today, but that will help them to any other exam other than the GATE examination. Any exam, if you write like ISRO, DRDO, Bharat Electronics, the Airport Authority of India, all these examination will contain the question from the electrostatic and magnetostatic. But in the GATE examination, there will be little bit less chance. It is not completely ignored. It is less chance. So there will be a sure short question from the other part of the syllabus, but their question may come from the electrostatic and magnetostatic as well for EC. Okay, so I think, sir, you are there.
Yeah. Yes,
So,
George, we will have multiple subjects keep going, like 2 to 3 subjects usually. So currently we have planned with mathematics, EMFT, and network theory. Clear? Because July batch, na, we have little less time. So usually 3 subjects will go and hands in on hands. Okay, thank you, sir, for your time and support. So we'll wind up this session, and
yes.
then we will start first class from tomorrow for engineering mathematics for July batch, and other batches already classes are going on. And then I will share your timetables Monday. Thank you, sir.
Okay. Thank you. Thank you, everybody.
So, hello everyone. How was the class? How was class, George?